Wasabi, you guys. Welcome to Integration Be Training for Advanced. In this section, the technique is going to be inversion. So, what is inversion? Inversion is where we let u equal 1 over x. And so this is where we started dealing with bounds like 0 to infinity. And then we have some function of something, and then with this u substitution, the bound remains the same, and the reason is because when you plug in 0, this is infinity. Well, this is technically the right hand side, so it becomes infinity, and then infinity here, plug infinity, you get 0, so you get infinity to 0, but then du is equal to 1 over x squared dx. The negative switches the bounds right back, so that's why we're able to have 0 to infinity and 0 to infinity here, because of that negative switching it back. And this x squared can also be written as u squared du. So pretty much what you have 1 over u squared du. And then we can get like some tricky stuff with it too, where you can add it together because we have the same bounds. So we can add it together. I'll just put a half there, and we can get something like this: u squared f of u plus f of 1 over u. Something like that. Now, to you, this looks like, this looks like a random horrifying integral, like I just made it worse. But there are many functions where adding it together actually simplifies it. So you pretty much uses this with functions that have this type of a specific certain property. Most commonly in this section that we're going to go over is logarithms. Logarithms have a thing where we have x, right? But then when you switch it to 1 over u, right, it has negative ln of, it becomes negative ln of u. And then we could do something with this, like, oh, this is I, this is negative I something, and it gets to that kind of tricky manipulation. So the logarithm isn't the only function that we can use. There are many other functions, a lot trickier ones. But for now in this section, for introductory, we'll be dealing with logarithms because they're the most easiest beginner-friendly integrals for learning inversion. Okay? Let's go ahead and get started with our first integral. Alright, we have this integral here, and to you it may seem like, okay, this looks awkward, like what do we even do here? So we're going to go ahead and let u equal 1 over x. And of course, I already showed you the bounds won't change. And then here we have 2 over x, right? Or 2 over u, but again, we can interchange the variables like we always do. However, not only we have 1 plus 1 over x squared, we have x squared coming from the du, remember? We have the 1 over x squared. So don't forget about that x squared that we have to add at the bottom. And with this x squared, this makes the denominator neutral. In other words, we have our denominator back. Okay? And now you can already see, oh, add this and add this, then we get from 0 to infinity, we get ln of 2x plus ln of 2 over x. Ah. And now, when you add these two, right, by log rules, 2x times 2 over x, that gives us ln of 4. So we end up getting, that's a 0, end up getting ln of 4, 1 over, ln of 4 over 1 plus x squared dx. And now this is a super easy integral. We know how to integrate this, right? This is just inverse tangent. So here we have half ln of 2, ln of 4 times, and then pi over 2, right? And in other words, the answer is pi over 2 ln of 2. And that is our answer. Okay, so now we have a logarithm, but then we have like a full-out quadratic polynomial. Okay, let's see. Let u equal 1 over x. Then we get ln of 1 over x dx. We have, let's see, 1 over x squared plus 2 over x plus 4 x squared. And this becomes, so now this gives me, let's see, if I simplify it out, 4x squared plus 2x plus 1. Ooh, this does not match with this. It just made the coefficients backwards. So how am I going to add this integral? How am I going to add and cancel everything? That's not going to help me. Dang. So we cannot use 1 over x. So then what? What do I do now? If 1 over x, if I can't let u equal 1 over x, then how am I going to handle this with inversion? So this is the most difficult case. There are some times where you'll come across this. And the majority of the times, a lot of integrals, it's just u equals 1 over x. But whenever we have like some polynomial here, you know, some very deceiving integral that we have to deal with, there are some times where we come across an inversion where the denominator is not the same. But how can we fix that, or how can we overcome that? So what we're going to do is u equal some constant of x. All right, now just hear me out. Okay, we're going to have a constant. We don't know what it is yet, but this is going to determine what we need to substitute in order to force this denominator to be the same. Okay, now just follow along very closely. Okay, this is the hardest part. Du is negative c over x squared dx. Okay, in fact, if we're going to let u equal c over x, x is equal to c over u dx, negative c over u squared du. Okay, in fact, I rather recommend you write it like this rather than the du, because you'll accidentally divide c, but it's actually multiplying. You're multiplying c. You're not dividing c. You're going to be multiplying c. Okay, that's like the biggest mistake people would do when doing constant finding with inversion. Okay, so then in that case, what we'll end up having is we'll get ln of c over x, technically, right? This is where people do like the biggest mistake, is because they focus here, and that's, you know, but it's actually this. They're the same thing, but the reason why I want you guys to be more attentive here is so that you know that you're using dx rather than du, where you accidentally divide c, but you are multiplying c. Okay. Now, here, let's see, of course, don't forget our dx, but for now we have c over x squared plus 2 over c of x plus 4, and then we have c dx x squared. Now if we simplify this, we have c 0 to infinity ln of c minus ln of x, and then here we have 4x squared plus 2cx plus c squared. Okay, now I want my denominator, I want this to look exactly like that, so that I can apply like an adhesion or King's rule, where, you know, I plus I, so that this and this cancels out. But how do I let this equal to this? Right. First off, we have x squared. So because we have x squared, I need that 4 to be factored out. Let me write this in blue. I need this 4 to be factored out. So I see that I have 2, let's see. Or you know what? Yeah, I'll write as 2 over 4. Then c squared over 4. Okay. All right. Now I really need it to look like this. This portion here must look like this. How do I do that? So we have x squared. I want 4 I want this equal to 4. Okay. 4 is equal to c squared over 4. This lets c equal 4. Now let's check it. Okay. Plug in 4 here, we get 2x, which is exactly what we want. Aha. C equals to 4. That is what we want. All right. C equals 4. You got it. So let's go ahead and do c equals 4. U is equal to 4 over x. Then x is equal to 4 over u. Dx is equal to negative 4 over u squared. This is just to give me a sign, or it's just to remind me. It's just a reminder. That's why I'm writing it down. So for less mistakes, you get 4 minus ln of x. Got 4. We have x squared, and then 4 squared over x squared. I'm gonna leave it as 4 squared. 4 over x plus 4. Okay. Now what we have is ln 4 minus ln x. Okay. Now we have 4 squared plus 4x plus 4x squared. And now we can go ahead and divide, factor out the 4, right? Which cancels out this coefficient. Perfect. Very perfect. And now ln of 4, ln of x. And we have 4 plus 2x plus x squared, which is exactly what we have. So now what we have here is this is I is equal to, from 0 to infinity, ln of 4 of x squared plus 2x plus 4 minus I. So what we have is we have 2y, or I guess we can go ahead and put as a half plus 2y, and then reciprocate the coefficient. ln of 4. I honestly would rather have it here. This is technically ln of 2. ln 4 over 2 is ln of 2. I just want to get that out of the way. Here we can actually go ahead and complete the square. So let's go and complete the square. That's going to give us plus 3. And now ln of 2, this gives us 1 over root 3, the inverse tangent of x plus 1 over root 3 from 0 to infinity. So now everything is just easy. Right, plug in infinity, we get pi over 2 minus, I'm going to put this here, the root 3 out of the way. Plug in 0, we get 1 over root 3. It's not 0 because we have this plus 1 here. So inverse tangent of 1 over root 3, that's like pi over 6. This would be pi over 3. And so our answer is pi ln of 2 over 3 root 3. Okay, this is our answer. Now it's very complicated. A lot went through just for the second integral. Yes, that's why this. I mean, this is advanced integration B. So, I mean, it's gonna be as ugly as this. But you know, if you need to, you can rewatch this integral, and you know, try to remember the process of how we solve this integral, right? Solve for the constant first, find a constant, right? Why are we finding a constant? Because when we let u equal 1 over x, it did not work, right? It did not work. We need to change our, we need to find a constant where the denominator stays the same, okay? And we learned that 4 over x helped, and then applied the inversion, okay? Oh god, we have an ln here and an ln here. This is very intimidating. Very, very intimidating. So, what do we do? Well, it's quite sus that we have 0 to infinity. Okay, so let's try 1 over x. Let u equal 1 over x. Then let's go ahead and we get 1 minus over x, 1 over x squared. Again, I don't know what I'm doing, I'm just experimenting what's going to happen. When I have x squared, I know it's going to come right back as 1 plus x squared, and then ln of 1 over x dx. Okay. Interesting. We have a negative ln of x here, so we know this is going to be a negative integral. But what is this on top? What is that on top? Here, 1 minus 1 over x plus 1 over x squared. What is that? What is that? X squared minus x plus 1? Oh, interesting. It's exactly what we have in the inside here. Okay, so what we have, technically, is we have a negative 0 to infinity, is we have 1 minus x plus x squared minus ln of x squared all over 1 plus x squared ln of x. Again, we have the negative here. That's a negative. Ah, this is awesome, because when we let this equal to I, this is technically negative I. So what we have is I equal negative I plus, the negative cancels out, 0 to infinity. This is technically 2 ln of x, 1 plus x squared ln of x. The ln of x cancels out. Nice. So now what we have here is this is going to become 2I. So I is equal to a half, 0 to infinity, of 2 over 1. Wow, this is so convenient. It's so convenient. I guess our answer turns out to be pi over 2. Okay? That was a very nice one. This was very satisfying, actually. A very satisfying cancellation. So that's our last integral for this section. I hope that this was very helpful of understanding how inversion works and how important and how helpful, how fast this technique is to handle some nasty logarithm integrals. Okay, that second integral though, definitely practice and get comfortable, but don't worry too much, as the majority of the times in most integration bees, you're just going to get problems like this, just letting u equal 1 of x. But then again, remember, test u equals 1 over x, and if the denominator, that polynomial in the denominator did not match, find a constant that could help cancel it out. Okay? Alrighty. Thank you so much for watching, and I'll see you guys in the next section.